Okay, so we're going to take a look at the Bohr model of the atom, sometimes known as the planetary model. And the basic idea that Bohr said is that he believed that electrons orbited around the nucleus in discrete energy levels, um, and they can't go out of those energy levels, so they can't spiral into the nucleus. This model works really well for things that have one electron, like hydrogen or helium with positive one charge, and he basically suggested that electrons differ only by their distance from the nucleus and the amount of energy that they had. So they could be closer or further to the nucleus, and they could be lower or higher energy level. Now what we can do is we can take a look at the Bohr atom, take a slice, and turn it into what is known as an energy level diagram. Now here we have what is known as the ground state, that should say ground state, which is the lowest energy level to the nucleus. And basically we have our energy levels going from lowest to highest energy level. And hopefully you can see as we get higher, our energy levels start to get closer together. Now, what happens is electrons can actually, according to Bohr, transition between these different energy states. And once they transition to a higher energy level, the atom is known to be in an excited state. There's specific names for the types of transitions that electrons can make, and it is your job to remember what they're called. So when we're making a transition from the ground state upwards to any level, where it's known as the Lyman series. When we're going from energy level 1 upwards, it's Balmer, and energy level 2 upwards, known as Paschen. Now, each of these different transitions actually require different amount of energy, and that different amount of energy can be seen in the type of light that they absorb. So let's take a look specifically at what Bohr did to come to his model. What he did is he had white light, which is made of all the different colors of light, and he shone that light into a bunch of hydrogen atoms. So gaseous hydrogen atoms, and he basically shone the light through and measured what kind of light, what color, what frequency, what wavelength of light was passing through my hydrogen gas. And so if we were to measure out his experiment on a graph, we would get 100% intensity of all the colors before passing through the hydrogen. And then he noticed after passing through the hydrogen, there was 100% intensity on all colors of light except for very specific colors of light. So we saw all the colors except for very few. And he also noticed that at higher energy levels for the light, the lines that were missing got closer together. So they did what we call converge, which is where the lines at higher energy levels got closer. And that's why he basically made this prediction that electrons can only exist in certain energy levels. And as those energy levels get higher energy, they start to get closer together. Now, below you'll see an image of the three series, Paschen, Balmer, Lyman. Remember that Paschen absorbs infrared light, Balmer colored light, and Lyman UV light. Okay, so I just wanted to add on to the end of the video because I'm not sure if I made it clear the idea of these emission and absorption spectrums. So absorption spectrum is the experiment that I talked about where we had our light shining through our hydrogen gas and we see that certain colors in the spectrum are being absorbed, the ones that correspond to the energy that the electrons are absorbing to go to higher energy levels. Emission spectrum, on the other hand, is when we take that gas and instead of shining light through it, we heat it up. And that hot gas with the heat allows its electrons to go up to higher energy levels and then they actually fall back down. And when they're falling back down, they emit specific wavelengths relating to where they fell back down from, and that's how we get our emission spectrum. You need to be able to explain the difference visually between these two spectrums, as well as explain what's going on with the electrons in each case.